Common sense would tell you that if you put a clock on the Moon, on Jupiter and on Earth, they would all tick at the same rate. It would also tell you that distances didn't change whatever speed you travelled at.
In 1632, Galileo published his principle of relativity, which was based on this so-called common sense. It said that the laws of physics are the same in any frame of reference. So, if you stand still or travel at 1,000,000 miles an hour, the laws of physics are the same.
But Einstein's special theory of relativity bases itself on something that certainly isn't common sense. It states that the speed of light is constant and independent of the observer. So, if you were standing still and a car moves past you at 20 miles an hour, the car is moving 20 miles an hour relative to you. But if you were moving at 10 miles an hour and the car moves past you at 20 miles an hour, the car is moving at 10 miles an hour relative to you. However, with light, you will always measure the speed of light at the same speed relative to you.
The theory states that time runs slower in a moving reference frame relative to an observer standing still, but this effect is symmetrical, so each person thinks the other's clock is running slow.
Take an example. If a man stands on a train platform, still, relative to the Earth, and the train goes past him, moving relative to him, the man on the platform will see the time slower in the train, and the man on the train will see time slower on the platform.
This can be shown by a light clock, just two mirrors with a light beam bouncing between them at the speed of light. If the clock is still relative to the observer, then the light just bounces vertically up and down. However, if the clock is moving relative to you, you see the light moving diagonally from one mirror to the other, so it must travel further, and hence the clock takes longer to tick.
It was eventually calculated that time slows down by a factor of gamma, also known as the Lorentz factor of time dilation. This is 1 if you are standing still, but increases to infinity as you approach the speed of light. So, time would be infinitely slower if you were to travel at this speed, and you cannot do so. The consequence of time dilation is quite staggering. It implicitly leads to an idea of phenomenon called length contraction. This is the idea that a person moving at a constant speed relative to you appears smaller than they would at rest, and the distance they travel also appears smaller.
This effect would mean that if we travelled at 99% the speed of light, distances would be around 7 times shorter.
The Large Hadron Collider at CERN is the most powerful particle accelerator in the world. By using superconducting materials, temperatures approaching absolute zero, and complex magnetic systems, scientists can fire particles travelling close to the speed of light in opposite directions with such precision that they collide. Experiments like this help us to understand the workings of particle physics in far more detail.
Because the particles in these experiments travel so close to the speed of light, the laws of special relativity need to be taken into account when calculating how much energy is released in the final collision.
The famous equation E equals mc squared is actually a shorthand version of E equals gamma mc squared. At rest, the two equations are the same, but near to the speed of light, such as in the Large Hadron Collider, this gamma is the key to understanding the energy present in collisions. This equation allows us to understand how every piece of matter contains massive amounts of energy. If we could find an efficient way to harness this energy, we could solve the world's energy problems overnight. Nuclear fusion opens this fast energy to us, but currently our technology doesn't allow us to get more energy out of the nuclear fusion than what we put in.
Einstein's theory of special relativity has given us a great insight into space and time. It has allowed us to understand physics from the macro scale all the way down to the micro scale. Currently, physicists are working on a unifying theory combining the complexity of quantum mechanics with the foundations of Einstein's work to give us the most insightful understanding of physics yet.